let phi from G to H be an isomorphism. Then phi of the identity is the identity. Moreover, for every group element, phi of G inverse is the inverse of phi of G. So not only do you preserve products, you preserve the identity and you preserve inverses. Hello, in this video we'll discuss some basic properties for isomorphisms. Some of these are not in the textbook because they're actually in a later section on homomorphisms, but I find them to be useful for some of the proofs to bring them up front and center in this section. One of the last things we prove in this video is that any two cyclic groups of the same order are isomorphic, and that is in the textbook. To show the first part, take any group element in G and multiply phi of E by phi of G. Because phi preserves multiplication, this is equal to phi of E times G. Because E is an identity element, E times G is equal to G. Likewise, phi of G is equal to E times phi of G because E is an identity element. And so what do we have? We have phi of E times phi of G is equal to E times phi of G. So by cancellation, we can cancel off the phi of G's on the right, and we see phi of E's times E. So what was the strategy we were actually using? Well, we know phi of E should be E, and so we know it should behave like the identity element, and so we were seeing that it does. But that alone was not enough. This part here is only showing that it behaves like the identity element for elements in the image of phi of G, not for every element in H. So that alone was not enough. By using this trick and using cancellation, we actually do manage to get what we wanted. So now we check inverses. The order here is actually important. How do you want to show that phi of G inverse is equal to phi of G inverse? Well, what's the definition of the inverse of an element? It says that when you multiply the inverse of an element times the element, you should get the identity. So if we want to claim that the inverse of phi of G is phi of G inverse, then we want to check that this product is the identity. Then the uniqueness of inverses will actually give us that this is the inverse of phi of G. So let's check this multiplication and see that we get the identity. Because phi preserves products, phi of G inverse times phi of G is phi of G inverse times G. Cancellation, that gives you the identity. By the previous property, phi of E is E. So phi preserves inverses. Another property I like to note is that phi of G phi preserves exponentials too. So phi of G to the nth power is phi of G to the nth power. We'll use this when we talk about cyclic groups. And the proof is by, at least for positive powers, one uses induction. So phi of G to the n plus first power, by definition, is the nth power of phi of G times phi of G. By induction, the nth power of phi of G is phi of the nth power of G. Because phi preserves multiplication, phi of G to the n times phi of G is phi of G to the n times G. But that's just the definition of phi of G to the n plus 1. So by induction, if you assume it's true for nth powers, then it's true for n plus first powers. Now how do you deal with negative powers? Well, you just replace n with its negative in a clever way. And so you have G to the negative n times negative 1. Well, phi preserves inverses. And we just saw phi preserves positive powers. And so, and negative n here is a positive number. And so you do actually have phi of G to the n is phi of G to the negative n to the negative 1. And then properties of exponents, you get positive n n again. Here's another interesting property about isomorphisms. That's simple enough and comes from these order calculations. Suppose you have an isomorphism between two groups, G and H. If you have a little element in G that has order n, then its image also has order n. So, proof. Let phi of G to the m be equal to e for some integer m. Then, by properties of exponentiation, the mth power of phi of G is equal to phi of the mth power of G. So you have phi of G to the m is equal to e then. That's also equal to phi of e by properties of isomorphisms. Since phi is injective, it follows that G to the m is equal to e. But since G has order n, that implies that n has to divide m. So, assuming that any integer power of phi of G gives you the identity, implies that that integer power has to be a multiple of n. So whatever the order of phi of G is, it has to be a multiple of n. Let's prove it's actually n itself. Phi of G to the n, by properties of powers, is phi of G to the n. Since n is the order of little g, then G to the n is the identity. By properties of isomorphisms, phi of the identity is the identity. So we see that the nth power of phi of G actually is the identity. So the order of phi of G is in fact n. And so we've seen that isomorphisms behave well with respect to powers. This one's actually stronger than the previous results because we actually have to use injectivity. And you get the exact same order. So this starts to tell you if G is cyclic, then H is going to have to be cyclic. We'll prove that again later with a different proof, but this is a shorter proof of that fact. But it starts to make you wonder whether or not all cyclic groups are of the same order are isomorphic, and that's something we're going to prove. Well, let G and H be finite cyclic groups, and suppose they have the same size. Then we're going to claim that they're actually isomorphic. Well, let's suppose that their order is n. Notice the same result actually holds for infinite cyclic groups, but I'm only going to prove it for the finite case. You can check the proof for the infinite case. It is actually very similar, and it's in the book. So suppose n is the order of G. Let G be generated by little g, and capital H be generated by lowercase h. Then a natural isomorphism would be given by sending G to the I to H to the I. One issue you have to check is that this is in fact well defined. Remember, exponentiation is not unique for cyclic groups. What I mean by that is suppose your group has order at 5, then G to the 17th power is going to give you the same result as G squared. You need to check that phi of G to the 17th is going to be the same as phi of G squared, because this formula we have right here depends on I. And I've mentioned this before, whenever your formula, your definition of your function, depends on something other than the element you're putting into it, you have to check that it's actually a well-defined function. So let's check that. Suppose that we have two different representations of our input. So G to the I equals G to the J. Two different powers that got us to the same element. We need to check that the resulting function value we get at the end of the day is the same, namely that H to the I is equal to H to the J. If that's true, then in fact this is a well-defined formula. It doesn't actually depend on I. Let's check that. Let G to the I be equal to G to the J. Then G to the I times G to the negative J is equal to the identity. By properties of exponents, this is just g to the I minus j. We're working with a cyclic group. So if g to the I minus j is equal to the identity, then that means that n divides I minus j. Since H is also a cyclic group of order n, and I minus j is a multiple of n, this tells you that the I minus jth power of H is also the identity. So here, starting with this equality, we managed to show that this I minus jth power of g is the identity. We're going to go the reverse direction with the h's. H to the I minus j is the identity. So by going the same steps in the reverse order, we see that h to the I is equal to h to the j. So in fact, even though we define this formula in terms of powers of I, it isn't well defined. It doesn't depend on I. It only depends on the element g to the I. In other words, phi of g to the I is in fact equal to phi of g to the j whenever g to the I is equal to g to the j. Moreover, we need to show this map is multiplicative. This would be step 2. Phi of g to the I times phi of g to the j. By definition, that's h to the I times h to the j. By properties of exponents, that's I plus j. By definition, that is the image of g to the I plus j. But that's g to the I plus j is just the product of g to the I times g to the j, and this is the multiplicative property. So phi is multiplicative. Next up, we show phi is injective. This looks very similar to the argument that it's well defined. Now we're assuming phi of g to the I is equal to phi of g to the j. And now we're going to prove that g to the I is equal to g to the j. And the argument's going to look very similar. What you see is that you now see h to the I is equal to h to the j. Therefore, by moving the h to the j over, we have h to the I times h to the negative j is the identity. By properties of exponents, h to the I minus j is the identity. Since h is order n, that means I minus j is a multiple of n. Of course, g has order n as well, so I minus jth power of g also is the identity because I minus j is a multiple of n. So unwinding, we see g to the I is equal to g to the j. So it's the same steps as the proof of well-definedness in reverse order. Finally, we have to show this isomorphism is surjective. Take any element in the codomain, it has to be a power of h. Well, just take the corresponding power of g. Phi of g to the I is equal to h to the I. So we have a surjective, injective, product-preserving function. It is an isomorphism. These two groups are isomorphic. As a corollary, a natural choice of H would be Z mod NZ. So in particular, every cyclic group is isomorphic to Z mod NZ, and vice versa. This particular map, the homomorphism, would have just been given by sending I to G to the I, by the way. And the textbook actually proves that particular example. But I find that going back and forth between addition and multiplication to be a little more difficult to follow. By doing it at the level of two abstract cyclic groups, everything is exponentiation. So I decided to do it that way. But it's essentially the same proof. If you work with the infinite group case, you end up getting that every infinite cyclic group is isomorphic to Z.